Section 8.6 has us working with solving rational equations. The second part of it also has us working with solving equations for a specific variable, but we're going to start with rational equations first. The first thing we're going to talk about is a small, subtle, but very distinct difference between when we're describing something as being an equation versus an expression. An expression is something that starts off with and contains an equal sign. An expression does not. So when we are working with something at the very beginning of a problem, we have to determine, is it an equation, meaning it has that equal sign, or is it an expression, meaning it does not have that equal sign? The main reason I mention this is because a lot of people will use these two words interchangeably. I'm probably guilty of this once or twice in the previous videos, but I want to make it clear that these are two very different things. In equation, you can actually solve for something. I can find x equals 10. I can find w equals negative 30. I can find L equals 1/2 n, something like that. In expression, we can't do that. At most we could do with an expression is simplify something down and condense things together. So I just want to make that clear because we go through some of these problems and people compare this section to previous sections. We think, well, they're all kind of the same, and therefore anything I've done in the past applies here, and it's not entirely the case. There is some subtle differences there. So I do think that is worth noting. So if you are going to be taking notes on stuff, I would say that is one that's worth noting, at least for the sake of having said you've seen it before. Now diving into the actual meat of this section, where we're actually solving rational expressions or rational equations. And see, there I go messing the words up. Rational equations. There we go. So I have a recommended process here. And as with all of the processes that I try and present to you, there are alternatives. But I've tended to find that this one, this method works great for a lot of people. Main reason why I recommend this process that we're going to go through is this process eliminates fractions. And I know fractions are one of the F words of math a lot of people don't like to use and don't like to work with. So that's one of the reasons why I really like this strategy, is it gets rid of those. And it opens up and kind of reverts the entire problem back to having an equation that has no fractions in it. And that tends to work better for a lot of people. So our first step, we need to determine all the values that create division by 0 anywhere in the equation. Where is it? There we go. Anywhere in the equation. This is also referred to as finding the domain restrictions on each side of the equation. So I want to find where is each denominator going to be equal to 0. Now my recommendation and hint for this is to fully factor all the denominators that have been given to us, and then set each denominator equal to 0. That's going to be where you're going to find any x values that equal 0, or t values, or whatever it might be with that variable. But that's going to give you those domain restrictions. This is technically an optional step, but I am going to show you where the advantages are of it later on in the problem. You might be looking ahead, but it's going to show up quite a bit here in example 5, and it's going to save us some steps down the road. But that's where we're starting. We want to find all the domain restrictions in the original equation. Looking at step 2, we're then going to find the lowest common denominator of all the rational expressions. So that means if I'm looking at all the fractions that I've been given, I want to find what is the lowest common denominator amongst all of them. And that's a very central thing to find, because in step 3, we're going to multiply both sides of the equation, meaning all terms, by this lowest common denominator. What we're going to find is a whole bunch of things are going to cancel, and this will eliminate fractions. And this is the main reason why a lot of people like this step. Now again, as mentioned at the very beginning, there are alternative methods to solve rational equations. Those alternate methods don't always eliminate fractions as quickly as this one. So if you find other methods online or other videos or stuff in books that give you a different way of going through those things, you're more than welcome to use those. But I think this strategy helps get rid of fractions, and because of that, a lot of people tend to like it. So once we have fractions gone, we're just going to have some resulting equation left over. Something equals something else, and then I can solve that using any and all methods I've learned. Maybe it's going to be just a linear function, x plus 1 equals 10. Maybe it's going to be slightly more complex than that. Maybe it's 2x minus 7 equals negative 30. Maybe it's a quadratic equation, and we need to solve that using factoring, or any of our other methods that we've learned. But step 4 is where we can kind of breathe a sigh of relief of I don't have fractions anymore, and I can just solve this thing with whatever I want. So we go through, solve that. We might get 1, 2, 3, 4 answers showing up out of this thing. Now step 5 is the kicker. We need to check the answers that we have. So you have two ways of doing this. If we have done step 1, where we have checked to see, okay, I found all x values or variable values that would create division by 0, then all I need to do is compare the answers that I get to the domain restrictions that were found in step 1. If any of my answers that I find are in those or listed in the domain restrictions, then I have to cross those out and not use those as my final answer, and then all the other ones are my final answers. If you have chosen to not find the domain restrictions in step 1, then the alternative is you absolutely must take all of the answers that you find and plug them back in to the original equation to see if the equation is satisfied. And if you're thinking on that going, oh man, I'm gonna have or I will be seeing or I am seeing some pretty complex and nasty looking starting equations, yes, that is why we do step 1, to save us a whole bunch of headache and a whole bunch of extra work at the very end of the problem. Of course, if you do not want to do that at the very beginning, then you are going to be plugging those in and you will need to check all of those values individually. So I'd pause the video here if you need to write down this process for yourself or make any additional notes. But otherwise, let's take a look at some examples. Starting off our first example, we're going to begin with step 1. So I'm going to determine all values that create division by 0 anywhere in this equation. The hint for this first step, factor all denominators to help with this. So I'm looking at each of my denominators, and I really can't factor anything. The first two are just numbers. The last one is just a monomial. I can't do anything with that. Okay, can't factor this thing. So I need to determine where division by 0 could take place in any of these denominators. Well, the first denominator is just a number, it's just 7, so I can't plug anything into that would create division by 0. Same thing with the second one, I can't plug anything into the number 3 and make it anything different, so we're good there. And then we look at this last denominator, and we notice it does have a variable in it, which means a value could be plugged in there. So I need to find where and what number would create division by 0 in this particular expression. Well, thinking on that, what number when plugged in for w would make w 0? Well, it's just going to be 0. So we might want to make a note to ourselves somewhere nearby that says our domain that w cannot equal 0. And that's all we need to really note on the domain at this point in time, which is fine. We're just making a note of it. Great. At the very end, we can come back and save ourselves some work with having to check things. So our next step then, step 2, says to find the lowest common denominator of the rational expressions. So I'm finding the LCD. Like we did previously, I'd recommend writing that down somewhere nearby for ourselves. So what is the smallest number that all three of these denominators, maybe it's not necessarily a number, but it's the smallest expression that all of these denominators could multiply into? And that's going to be 21w. Remember, your nuclear option with finding the lowest common denominator is to multiply everything together. It works well in this case, not always with others, but it is something that you can do. Moving on to step 3, we're then going to multiply both sides of the equation, meaning all terms, by this lowest common denominator. Now, when you are doing this, I recommend, it might seem like it's a lot of extra work and a lot of extra writing, but trust me, it's going to save you a lot of headache down the road. Actually write out every single thing being multiplied by this lowest common denominator. The reason we do this is because each individual term that we have, each individual fraction that we're starting off with, is going to cancel with this lowest common denominator in some unique way. It doesn't mean that there can't be repeats of how things cancel out. That happens fairly frequently, but it does not mean every single thing is going to cancel the same way. So what we're looking at with this is, well, going to do some cross cancellation here. I have two fractions multiplying together. With my first one, I'm seeing that I have a 7 down below and a 21 up top. I can cross cancel those out. 7 becomes a 1, 21 becomes a 3. Looking at the second one, I have a 3 in the denominator, 21 in the numerator, so that's the 3 is going to become a 1, 21 becomes a 7. And then for my last one, I have a w in the denominator spot, w in the numerator spot, so I can cancel each of those out, and those each become 1. Now again, the advantage of this, as we're noticing, is all of my denominators have just become 1. So now I can rewrite each of these things to instead be 9w, just multiplying things together here, plus, oops, clicking the wrong things here, plus 14w, these parts multiplying here, equals 21. And again, just these parts multiplying here. And now, again, the great advantage of this process, we have completely eliminated fractions, and we can solve this resulting expression or equation in any way, in any method that we want to. I'm going to make this 9 a little bit nicer because it almost looks like an A. Here we go. So we have 9w plus 14w equals 21. We're just going to solve this our standard way of solving linear equations. Combine like terms on the left side. I'm getting 23w equals 21. I'm then dividing both sides by 23. Whoops, 23 to get w by itself. And I'm getting 21 over 23 as my potential final answer. So that was step 4, solving the resulting equation. Now step 5 says we need to check our answers. Compare any answers to the domain restrictions found in step 1. So our domain restrictions that we have up here tell us that w cannot be 0 for a final answer. Well, we found w to be 21 over 23, which means that what we have isn't listed in our domain restrictions, and therefore is an actual final answer that we could have. And there we go. Our answer for number 1 is going to be w equals 21 over 23. Looking at our second example, we're going to follow the exact same process we did with the first. First, want to determine all values that create division by 0 anywhere in this equation. So I'm looking at all of my denominators, seeing where I have variables showing up. So I have no variables showing up down here. That 1 is implied to be over 1 as a fraction. I'm looking at my second one here, and I have a variable there. I have a variable here. So I need to find any domain restrictions that are showing up in 2 of these rational expressions. So looking at our first one, n. What value when plugged into n is going to create division by 0? Well, that's just going to be 0. Okay, well, you know n can't be 0. Maybe we're going to have a second or third number showing up with this. Taking a look at n squared, what number when raised to the second power, or when multiplied by itself, equals 0? And that's also going to be 0. So turns out that while I have 2 denominators with variables, I'm still only going to have 1 domain restriction. And that's fine, that happens. But step 1 is done. Good to go there. Taking a look at step 2, we're told to find the lowest common denominator of all rational expressions. Okay? So looking at all three of these things, what's the smallest thing that all of them can multiply into? For these, that's going to end up being n squared. I can't factor any denominators at all because they're all monomials. So, okay, best I can do is use n squared for all of these. So step 3 is then saying multiply both sides of the equation, meaning all terms, by this lowest common denominator. Again, I recommend as you were going through this to actually write out for yourself each individual thing being multiplied by this lowest common denominator. And then for each of these, we're going to find that something is going to cancel with the lowest common denominator and the other denominators that are listed here. So for our first one, well, nothing's going to change. The denominator, again, is implied to be 1, so nothing's going to change there. For our second one, we're going to have one of the n's cancel in each of those. And then on the right side of the equation, I have an n squared and n squared. Those are going to cancel. They each become 1. And now all of my fractions have been eliminated. I'm now left with n squared plus 4n equals 21. Again, just multiplying what's left over here. If you need to, there's nothing wrong with this. We did it in example 1, so if you want to write these out like this, you can write your lowest common denominator as being over 1 as a fraction, if that'd be helpful to you. You don't need to, and you won't always see examples listed like that, but it is something that you do have the option of doing. So now from here, we're just solving this resulting equation, step 4. And I'm looking at this going, I'm going to need to get everything onto one side of this equation. And I'm going to solve this thing using factoring. So I need two numbers that multiply to be negative 21 and add together to be positive 4. Those numbers are going to be positive 7 and a minus 3. So now I need to solve each of these individually. I'm going to move us up just to give myself a little bit of space here. So I'm splitting each of these up and I'm determining where is this n plus 7 going to be equal to 0, and where is this n minus 3 going to be equal to 0. So I'm subtracting 7 for the first one, then n is negative 7. For the other one, I'm adding 3 to both sides, and I'm getting positive 3. Now before I say these are my final answers and I'm done, again, step 5 says we need to check our answers. Compare any answers to the domain restrictions that we found in step 1. So are either of these numbers that we found here listed in our domain restrictions? No, they aren't. So therefore, we have our two final answers. And you'll find that it's fairly common with a lot of these problems where you can have 2 answers, 3 answers, sometimes 4 or 5 answers, but most commonly with what we're going to be seeing, you're going to be having probably 0 to 3 answers showing up most commonly. But otherwise, for number 2, final answers are n is equal to negative 7 and n is equal to positive 3. Looking at number 3, we're starting to get into problems that are a little bit more advanced and we have a little more complicated things showing up here with our denominators. So step 1 is still telling us we need to go find all values that create division by 0. We need to find those domain restrictions. So I need to find what value of t would make this denominator 0 and would make this denominator 0. Both of the denominators have variables in them, so I'm going to probably have 2 different domain restrictions in here. Might just be one, like we had in example 2, but we need to check each of them individually to make sure. So sometimes doing this off to the side can be very, very helpful. Again, I'd list somewhere for ourselves the domain. So what values can t not equal? So let's look at our first domain. So I want to find where is t minus 6 going to be equal to 0. I add 6 to both sides. T equals 6. Okay, so that tells me that if 6 was plugged in to this expression, denominator here, that would create division by 0. So therefore, part of my domain restriction is that x cannot equal number 6. Looking at just t, on the other side, well, as we've done and seen with previous examples, what value when plugged in for t would create division by 0? That's going to be 0. So we have our domain restrictions of t cannot equal 6 and t cannot equal 0. Excellent. Moving on to step 2. We're told to find the lowest common denominator of all rational expressions. So we have a binomial showing up here and a monomial showing up here. So our lowest common denominator for these, better D there. Our lowest common denominator for these is going to be t times t minus 6. And again, you can make a note of this wherever you need to off to the side. I'm actually going to move this a little bit, only because I'm running out of space and I might need to rewrite some stuff there. We'll divide these here a little bit just to make it clear. Okay, so we found the lowest common denominator for ourselves. That's going to be t times t minus 6. Step 3 says to multiply both sides of the equation, meaning all terms, by that lowest common denominator. And we're starting to get into some of the examples where we're going to see something much larger multiplying out now. You might think again, that just seems like a lot of work to write all of that. If you're able to keep track of it and do it all in your head, or do a good portion of it in your head, you're welcome to do so. But I think writing it out makes it way clearer, a bit more obvious what is going to cancel in our next steps now. So we multiplied everything out. We want to eliminate fractions. For the first set of stuff, I'm noticing there's a t minus 6 that can cancel. Those each become 1s. On the other side, I have a t and a t that can cancel. Each of those become 1s. And then I figure out what the resulting equation is going to be. On the left side, I'm going to have 3t once everything multiplies together. And on the other side, I'm going to have t minus 6. So fractions are gone. Great, I can solve this thing normally. So I'm going to go through, and I'm going to subtract t on both sides because I want to get t all by itself. So let's get it all on one side. So I get 2t equals negative 6. I'm dividing both sides by 2. And I'm just going to put this off the side here. I'm getting that t is equal to negative 3. So great, we have our potential answer. Now step 5 says to check your answers, compare them with the domain restrictions in step 1. So is our potential answer listed anywhere in our domain restriction? No, it isn't, which is great. So therefore, we have our final answer for this problem as t equals negative 3. Our final example is going to have us have to do a little bit more intensive work with this. We're still following the same steps, same process, but there's going to be a little bit more work involved. Looking at number 1, or should I say step 1 of our process, we're determining all values that create division by 0 anywhere in this equation. The hint that's listed this is to factor all denominators. So I'm looking at my first two denominators and seeing, well, I can't really do anything to factor those at all. But this last one, this is the difference of squares, so I can factor that last denominator. It's a very good habit to look to see if I can factor things before we find the domain restrictions. Again, that hint in there is there for a reason. previous problems that we had, we couldn't factor anything, so we didn't have to. But in this one, we can factor things, so I think it's worth doing. Make this a better minus 11 here. There we go. So now, for our domain, we want to find any a values that would create division by 0. So I'm looking at my first, second, and third denominators. And I'm seeing that looks like this first denominator and that last one have something in common. And then my second denominator and the last one also has something in common. So while I have three denominators that have three denominators that have variables in them, I kind of only need to find where these equal to 0, and those same domain restrictions are going to apply to this one. So what value of a when plugged in here would create division by 0? That's going to be negative 11. So a cannot equal negative 11. What about over here? What value of a when plugged in would make this denominator equal to 0? And that's going to be positive 11. And with our last one, we would need to separate these things and say, where is this thing equal to 0? Where is this thing equal to 0? But it turns out that that just creates the two problems that we had there, which we've already found the domain restrictions for. So some of that extra work already done for us. Excellent. Step 2 says we need to find the lowest common denominator of all the rational expressions. So again, listing that somewhere nearby for myself. The lowest common denominator for this entire thing is going to end up needing to be, looks like it's going to be a plus 11 times a minus 11. Okay. And that means then that every single term that we have is going to need to get multiplied by that lowest common denominator. And I'm going to note here, just for the sake of showing it, you can use and alternate between having brackets and parentheses written in here. I find that particularly helpful when we have multiple grouping symbols showing up. So I'm still multiplying by the lowest common denominator. It's just using a slightly different way of organizing it to show where some parentheses start, some parentheses end, or where some grouping symbols start and some grouping symbols end. If you'd like to use only parentheses with this step, you can do that. If you want to use a mix of parentheses and brackets, kind of like I'm doing, you can do that also. I use the mix only because I sometimes mix up where one parenthesis starts, one ends, things like that. So it helps me keep it organized. But now that I have everything written out, now I'm canceling things. I'm seeing in the first one, I have this a plus 11 that cancels out. Those each become 1s. For the second one, I have a minus 11s. They're canceling out. And then in the last one, the entire thing cancels out, which is rather nice. And now, what's my new equation going to look like? Well, I now have 9a minus 99. Again, that's these remaining things multiplying together, plus 6a plus 66. Again, that's these remaining things multiplying together. And all of that equals 7. Just everything left over here multiplying together. And now I'm solving the resulting expression, or resulting equation, I should say. So simplifying each side down, the left side of this equation, I'm combining like terms, and I'm going to get 15a minus 33 equals a positive 7. I want to get a all by itself, so I'm going to add 33 to both sides. I'm getting 15a is equal to 40. Trying to get a all by itself, so I'm going to divide both sides by 15. And I'm getting that a is equal to 40 over 15. Now I always need to reduce fractions down as best I possibly can. I think 5 is going to evenly divide into both 40 and 15. So I can reduce this down to be 8 over 3. So we just did step 4, solve the resulting equation, and we got a is equal to 8 over 3. Step 5 says we need to check our answers and compare that with the domain restrictions. So we have a potential answer of a equals 8 over 3. Let's zoom this out just a little bit so we can get our domain restriction in the picture as well. Okay, it looks like our domain restriction says that a cannot equal negative 11 or positive 11. Now, our answer is neither of those, so great. We have our final answer here. And we are good to go with example 4. The second part of 8.6 has us working with solving for a very specific variable. The big thing to note and remember when you are solving for a specific variable is that we are able to add or subtract, multiply or divide all variables as if they were just numbers. So we're going to see generally 2, 3, 4, 5 different variables all showing up in one single problem. Somewhere in the problem, it has to specify for us what are we solving for. We're given an equation, solve for x. We're given an equation, solve for n. Given an equation, solve for r. Something along those lines. So all of our previously learned methods for adding things, subtracting things, multiplying or dividing things are still in play. All of the things that we have learned previously about eliminating fractions is also still in play here. So we can use any and all of our previously learned methods to go through and solve these things. Again, I'm kind of repeating myself on this because a lot of people think that there is a very specific set of rules that we need to follow when solving for a specific variable. There kind of isn't. So there's a lot of the same stuff that we've used in the past. We're just using it in a more generalized sense than using specific numbers is all. The other thing I want to note, when you're going through and solving for a specific variable, most answer keys are going to want you to leave your answer as a rational expression, which is perfectly fine, but not as a complex rational expression. So if I have fractions inside of fractions, I need to simplify that down. And that would be using the 8.5 material that we discussed in a previous video to help with that. Now the last thing I want to note before we dive into our two examples that we have here is a massive warning with these. You will see problems, maybe not necessarily these examples, but you will see problems in the future where you will have two variables, one being uppercase, one being lowercase. So as an example, maybe you have a lowercase m and an uppercase m. When you are going through problems and you're solving for a specific variable, you can absolutely never change a variable from upper to lowercase or vice versa on a whim. This variable in a problem might represent the mass of a smaller object. This m in that other random equation could represent the mass of a larger object. So if you're just going to switch these things back and forth, well, in the context of a problem, that's really important. That's two very distinctly different things, and we can't just switch those around vice versa as much as we want to, especially on a whim. So just want to make that note now that as we are going through the examples that are listed here, and as you are going through problems on your own, you can never change uppercase to lowercase or lowercase to uppercase. Even if that might make something a little bit easier to look at, you still do not want to do that. So with that noted, let's dive into our two examples here. So our first example here is giving us the equation L over R equals P. And we're told that we need to solve this thing for R. Now my recommendation to you when you are writing and going through these problems, my recommendation is write this whole thing out for yourself, including the part where it states what you're solving for. Me personally, I like going a step further. I like circling and underlining that specific variable, because I've seen very often people will be given something and they will solve for a variable that they think is very easy to solve for, but not necessarily what the question is actually asking them to solve for. So we want to make sure that that's very clear and apparent for ourselves. So I'm solving this equation for r. r is currently in the denominator of this fraction. So we have a couple options with this. We can either just try to get the r out of the denominator spot, or we can eliminate fractions entirely using what we did in our previous part of this same section. Now in this case, it's not really going to make a huge difference in what we want to do with that, but it is one of the routes that we can take. The other route that we have is to notice that this right side, well, it's just written as a single p over there. It is implied to be a fraction. So I now have an instance of a fraction equals a fraction showing up in this problem, which means the option is available to me to do cross multiplication here. So if we're looking at this one problem, right there's about 3 different strategies that we could use to solve this thing. Any and all of them will work. It's really your choice on which one you would like to use. So I'm going to use the one that's similar to what we did previously, which is I'm going to identify what is the lowest common denominator between everything in this problem. So the LCD for this is going to end up being r. And I'm going to multiply both sides by that lowest common denominator. Again, my intention with doing this is specifically to get rid of all fractions in this problem, and then I will solve for what's left over. So on the left side, I'm getting that the r's cancel out. On the right side, nothing cancels, but hey, nothing else, my resulting expression now doesn't have any fractions in it. So I'm getting L equals P times R. I want to get R all by itself. That's what I'm solving for. So I need to divide both sides by P. On the right side, those P's cancel. And what's left over? I have L over P is equal to R. And there's nothing else I can do from there. So I now have my fully reduced final fraction answer. Now, for the sake of just seeing an alternative method, I want to go through and mention the one of if we had used cross cancellation with this. And again, this is just to see that there are multiple routes that we can take with this. So again, just noting what I'm solving for. Again, for me personally, I like circling, underlining, and making it clear. So I'm going to rewrite this thing. So it's really clear to me that this is a fraction equaling a fraction. And because it's just a fraction equals a fraction, I can now do cross multiplication. So when I do that, I'm going to get L times 1 equals R times P, which gives me L equals PR. And then just like the left side, I'm dividing both sides by P. And I'm getting L over P is equal to R. The P's cancel on the right side. So again, as you're going through these problems, multiple routes that you can take with them. There's lots of different strategies at our disposal, which is both the nice and kind of frustrating thing is we can do a lot. So at the end of the day, we just need to pick a strategy and commit to it for that specific problem. But as we can see here, no matter which method we choose, we're going to get that R is equal to L over P. Looking at number 2, well, we're going to have a little bit more that we're going to have to do with this. We're asked to solve for A, and A is currently in the denominator of a fraction, and I have some other fraction stuff that's showing up over here on this side as well. So I'm looking at this and I'm thinking, okay, I've got a few options. I can try and move this B divided by 5 to the other side, but that doesn't, I don't know, that A is still trapped in the denominator spot, and that seems like it's the biggest issue at this point in time. So I'm going to go with the approach of I'm going to try and eliminate all fractions that I have. I might not make the thing any simpler in this terms of where the A ends up. Maybe it's going to end up on this side and still be over here. I don't know. I will deal with that later, but I just want to get the a out from the denominator spot, if nothing else. So I'm going to eliminate fractions, and that's what I'm choosing for this problem. So what's the lowest common denominator amongst everything that we've been given? That's going to be 5a. So that means every single term, I'm just going to move this just off the side so I have a bit more space here. So I'm going to take each term in this problem and I'm going to multiply it by 5a. Again, my intention for doing this is to eliminate fractions. I don't know what's coming after that, but at the very least fractions will be gone, and that's probably going to make things at least a little bit nicer. So on the left side over here, well, nothing's going to cancel, so I'm just going to get 5ac. Got a better 5. There we go. I'm going to get a 5ac. For our next one, I have an a in the numerator and a in the denominator spot, so those cancel and each become 1. So this thing's going to become 10. And then on that last term, I have a 5 in the numerator, 5 in the denominator, those cancel. And then I'm going to be left with AB. All right, well, it's not necessarily a whole lot better, but at the very least, I now don't have any fractions left over, so that's nice. So going back to what we're solving for, we're trying to get a all by itself. Now I'm noticing I have a in a term on the left side and a in a term on the right side. I want to get all of my terms that have a in them on one side of this equation, and I want all other terms that don't have a in them, namely this 10, all on the opposite side. So to do that, I'm going to subtract AB from both sides of this equation. And again, you might look at this and say, well, I can't combine any like terms on the left side. I've got an AC term and an AB term. And yes, that's accurate, but we're just trying to get all of our A terms by themselves. And now that I have all of the A terms, or terms that contain A, on one side of this equation, now I can do the really tricky and crafty thing of I can factor an A out from both of those terms. So if I factor that A out, because that's the thing I'm solving for, what's left over? I have 5c minus b left over there. And now I'm looking at this thing, better 5, and I'm saying I have the variable a, the thing I'm solving for, multiplied with something. Now this something is a big, maybe gross looking binomial, but as listed in our notes, we can treat all variables as if they were just numbers. So this whole binomial that I have here, that might as well be the number 10 or the number -3 or +7. So I can divide by that. Oops. Computer's glitching a little bit more than usual here. There it goes. So on the left side, the 5c minus b is going to cancel. And on the right side, well, nothing's going to cancel over there. And that's fine. So what am I getting? Well, on the left side, I'm left with just a. On the right side, I have 10 over 5c minus b. The 5s are just not showing up very well here today. Okay, there we go. And I'm looking at this right side of the equation and I'm saying, can I do anything to reduce this down or cancel anything out? You might be inclined to say, well, I have a 5 down below and a 10 up top. I can cancel those. And I'm going to say, you have to pause there. If we want to cancel, what do we need to do first? Remember back to our previous notes, we need to factor, then cancel. If we cannot factor anything, then we cannot cancel anything. So I cannot factor anything from the numerator spot. I cannot factor anything from the denominator spot, and therefore I cannot actually cancel anything out. So I'm forced to leave this thing in its form that's written in now, making my final answer for this problem A equals 10 divided by the quantity 5c minus b. So as a quick recap of all of the stuff that we discussed in our section for today, we had our process for going through and solving rational equations. We had our examples listed here with the answers going along with those. We also worked with solving for a specific variable. Again, the big thing we want to note and remember with this is that we can add, subtract, multiply, divide variables and everything just like we would with numbers. We have lots of options at our disposal as we're going through these as well. If you do want some extra practice, I'm going to scroll this down here. And I'd pause the video here if you want to try some of these problems by yourself or with someone else. And then we'll scroll down and get you the answer to these questions now. And there we have everything for the 8.6 material.